So we will start with that one of the problems that people have asked for discussion in as a doubt. It's a kinematics problem. Okay, so example one for today is this one. You have that pretty standard situation of three particles at the corners of a triangle. Say A, B, and C, and they start at t equal to 0, precisely with velocity such that they are all chasing each other. So initially the velocity is like this. So all three have, so A continuously points at B with, sorry, not B vector, at the particle B with uniform speed of V. And similarly, B continuously points at C with a uniform speed V, and C continuously points at A with a uniform speed V. So in this case, we have to find the distance traveled by any one particle as it completes one revolution or one rotation around the centroid of the triangle. Okay, so we have to calculate this quantity. So this is basically, since we are talking about angular displacement of 2 pi completing one rotation, therefore hence basically we are talking about the relationship between distance and angular rotation. And since speed is constant, so distance is directly proportional to time. So basically we are talking about angular displacement versus time. So from the beginning you understand that what we have to do is we have to somehow understand the angular motion of the particles around the centroid. Okay, so let's get started on this. So as you all know that in this case, if they start from this position at t equal to 0, then for example, after a very short duration of time, so this is where they were at t equal to 0. Now after a very short duration of time, let's say t equal to delta t, where delta t is a very short time, the particle B would have reached here, the particle C would have reached here, and the particle A would have reached here, because they are traveling like this. So now they will form a new triangle, which is again equilateral. So if in the original triangle, the initial distance between them was, let's say, L each. So now after delta t, they are forming a new triangle where the distance between them has reduced to L minus B delta t, like this. Same thing here. So now A is here, B is here, C is here, and now their velocities have changed direction. A is pointing like this, B's velocity is pointing towards C, and C's velocity is pointing towards A. But you see something interesting here, that it still forms an equilateral triangle. So a little while later, when A is here, when B is here, and when C is here, they form a new equilateral triangle, and like this. And all the time the equilateral triangles maintain the same centroid. The centroid remains fixed. So basically A, B and C follow curvilinear paths such that their mutual orientation is always an equilateral triangle. with the fixed centroid. The centroid is not moving. The centroid is remaining fixed basis. Okay. So that's one interesting point. The other thing is that, so after some further amount of time, let's say t equal to t, the part they have probably reached, let's say somewhere like this now. So A has gone on this kind of path and reached here. B has gone on this kind of path and reached here. C has gone on this kind of path and reached here. Okay. But still, the velocities are maintaining that orientation. So when you visualize this and you take the case of any random situation, okay, when their orientation is, let's say, something random like this. Let's say by now A has reached here, B has reached here, and C is here. With respect to the centroid, you'll realize that the relationship between the velocity vectors in terms of angles remains fixed. So kya ho raha hai? Always A's velocity vector is towards B, B's velocity vector is towards C, such that this angle is always 60 degrees. C is towards A. And also, if you look at any one particle, its velocity vector is always at 30 degrees with respect to the origin. So this is the kind of thing. So two things you can observe over here is that approach velocity of A to B or B to C or C to A. So approach velocity of particle to particle is always this. Okay. So this is uniform. So if the side length at any time t of the triangle is x, then that tells you that minus of dx by dt is 3v by 2, and that therefore tells you that delta x is always minus 3v by 2 delta t. So from this you can see that by the time they come at the origin, your delta x should be minus L. So that's how you calculate the time of collision. That is, I'm sure, a problem you've done before. The other thing that you observe is that the approach velocity of E towards the fixed centroid or B towards the fixed centroid or C towards this fixed centroid, that approach velocity is also a fixed quantity. The approach velocity of particle towards centroid, that's always equal to V cos 30. So now you can see that the distance from the centroid, if this is x, it will be how much at any point of time? Okay. Let's say the distance from the centroid is z. So minus of dz by dt will always be equal to root 3 by 2v, where z at any point of time is x by root. So delta z is equal to root 3 by 2 v delta t with a minus sign. So again, when collision occurs, so at collision time, your delta x is equal to minus L or delta z is equal to minus L by root 3. So the time will become L by 3. So this is something you are already aware of. Okay. So I'm not getting too much into the explanation of this. Just leave you with a moment, like with these two aspects of its motion. But now we have to also think in terms of the angular motion of any particle around the centroid. Okay, so hope this is all clear. This is standard stuff that you're used to. Now let us come to the part which is relevant for this particular question. So let us see instantaneous angular velocity of a particle with respect to a point. There are a couple of ways to understand this. Okay. For example, with respect to a point over here, if I want to understand that a particle which is right now located at the position R is having a velocity vector v. Like this. So this particle P has an instantaneous velocity vector v. So what do we mean by this thing? The instantaneous angular velocity about the fixed position O for the particle P. So basically what we mean is that if we have drawn some standard coordinate frame like this over here, which is fixed to the point O, then we would have seen that this theta is changing. That is what we mean by this quantity. So this quantity is rate of change of theta. So what you do over here is that the easy way to understand it is that you divide your velocity into components, the radial component and the tangential component. So if your angle between the position vector and the velocity vector is some beta, let's say, then what is happening over here is you can see that beta being the angle between the position vector r and the velocity vector v. You can see that r cos beta is the radial component of velocity. And r sin beta becomes what we call the tangential component of velocity. So further you understand that as this particle is moving, the radial component of velocity is the rate of change of distance from the center, whereas the tangential component of velocity becomes nothing but r into d theta by d. This is the concept. Because you would see that next moment if the particle reaches somewhere here, that means its distance is also increased. This has become r plus dr, but its angle has also changed. So this has become theta plus d theta. So in general, that is how we express. In other words, we take a differential displacement as something along r cap plus something along theta cap. So you can see that velocity will become dr by dt r cap plus r d theta by dt theta cap. Okay. So in fact, this is one of the things I will be discussing about more today: radial coordinate system and how to write various quantities, including gradient vector and all that. But for the moment, this is enough to understand over here. So d theta by dt will have a magnitude. Okay. We'll talk about plus minus later of that v sin beta divided by r. Okay. This is the general thing. Another way you can understand this is another method to understand is that angular momentum of the particle is r cross mv, and angular momentum is nothing but instantaneous moment of inertia. Okay. So again, if you take mod on both sides, this actually becomes mr square into d theta by dt's mod is equal to mvr sine theta. So it comes back to this. In fact, it's the other way around actually. Angular momentum is defined because of this kind of relation. Okay. So now coming back to that, so the third point you can see in that situation is that at any instant, any particular particle, for example, I'm taking V over here, its velocity vector is always making an angle of 30 degrees with the line joining it with the centroid. And remember, the centroid is a fixed thing. Okay? So about the centroid, it has an angular velocity. So for any particle, like the particle B over here, we have taken d theta by dt's mod about the centroid. That will become how much? It will become tangential component of velocity divided by instantaneous distance, which we have taken as z. Okay. So tangential component of velocity will become v sine 30 divided by z. So this is your d theta by d. So you can see here that the tangential component of velocity will be this one. This will be the tangential component of velocity. This will be the radially inward component. So in fact, you can see here the radially inward component, which is v cos 30, is actually minus dz by dt, whereas the tangential component, which is v sin 30, is actually z d theta by dt, because z is the instantaneous distance. So it's like we are using these two equations now. We're going to use this equation along with this equation. Okay. So this is telling me this, that d theta by dt is v by 2z. So now in order to solve this, I need z as a function of time. So that will come from where? That will come from this. So root 3 by 2v is minus dz by dt. So these two equations now we will have to handle simultaneously, so that we can. So from this one on the left, we'll get z as a function of time. So dz is equal to minus root 3 by 2v dt. Now integrate this from initial value of z, which was L by root 3, to some instantaneous value, which is z. So you'll see L by, or z minus L by root 3, we'll take the minus sign later. ये कितना हो जा रहा है? Minus root 3 by 2v t. So z as a function of time is becoming L by root 3 minus root 3 by 2v. So z as a function of time is like some, you can say capital A minus b. It's a linear function where a is L by root 3 and b is root 3 by 2. Okay. So let's substitute this there now in equation 2. That will show me that d theta by dt is v by 2 a minus b. So now there is a standard kind of integration. You integrate this to find the time in which it is rotated by theta. So time going from 0 to t, theta going from 0 to some delta theta, the angular displacement. So delta theta will become v by 2. When you integrate this, you have that minus of ln e minus vt going from 0 to t. So this is that standard kind of integration that you are aware of. So this term will now become minus 1 by b into v by 2 delta theta. Okay. So now you want to find the time at which delta theta is equal to 2 pi. So just substitute that. Yes. Okay, so E by B we can check out from there what it was. So E by V will see is the total time of collision only. It will be 2L by 3V. There's also V by 2 here. This term, just a moment. This term will be, you're transferring this term, so 2V by V. This kind. So that 2V by V will become how much? B was root 3 by 2 V. So it will become root 3 into 2 pi. B was root 3V by 2. Alright, so this gives you the time. So this distance will be speed into time. This should become your final answer. Okay. So hope the working part is clear to all of you. This also shows you something interesting, that in principle the time versus the angle relationship is very interesting. We'll come back to that, but first just make sure you get this. Okay, people, so hope the working part is clear. Okay, so I'll send you the entire note, so don't worry about that. Okay, now before we move on to the next thing, the aspect I wanted to bring to your attention, what is very interesting here is the relationship between time and angle. If you see this relationship. Okay. Now actually this E by B is nothing but the total time when the collision happens. So this time is this kind of a function of theta. Okay. So if you really think about it here, it's very interesting that if you look at the relationship of time versus angular displacement. This is your delta theta versus time. Now, if this is the total time when the collision was to happen, capital T is that 2L by 3V, that is the collision time. You will see that it makes infinite angular displacement. The graph of this thing will actually be like this kind of thing. It will be exponentially. So this time is equal to capital T into 1 minus e raised power minus some constant into t time, where capital T is this and that constant we just saw was 2b by v or something like that. Okay. So in fact, what it means that delta theta tends to infinity as t tends to capital. So extremely large number of rotations. Before impact. So that's one interesting aspect. So basically, you have to visualize that equilateral triangle, it keeps getting smaller and smaller and smaller. So as it keeps getting smaller in size and it's rotating, okay, the number of rotations is actually infinite. So that's another interesting aspect of this kind of problem. Okay, now let's come to some examples I wanted to discuss today. Examples related to potential energy and internal conservative force, or electric field and potential, that kind of thing. Basically, examples that are based on the relationship that delta U is minus of F dot ds, or internal conservative force is negative gradient of potential, which of course in component form you write as this. And likewise, if there's a Z component, that also. Okay, so let's start with some questions related to this. So now a force acting on a particle moving in a two-dimensional XY plane is given by, so this million. Yeah, so given by this where alpha and beta are constants such that x and y are in meters and the force is in newtons. So we want to calculate the work done by this force as a particle moves along the path ABC shown in the diagram. This is the first part of it. So now let's come to the diagram. Okay. And second part, show that the work done by the force head for any path from A to C is identical. The second part basically you have to show that the force is conservative. So you take any path from A to C, the work done will be the same. Let me minimize this and try to work this out. So just try this out. There's just one small correction. There will be a 3 here in the denominator. So you should get the answer in terms of alpha and beta. Just try this out and tell me how much the answer is. Anyone got the answer yet? Bhaskar, that E and B is alpha and beta. No, no, actually, unfortunately, your answer is not right. Yes, Ananya, correct. Okay. Just to give you a bit of hint that the final answer for the first part and the second part both, for the given coordinates of A and C, what will happen is it will be independent of alpha. It will only depend on beta. Okay. So let's understand this question backwards. That is, first let's prove that it is independent of path. So the force is given to us as some x component plus some y component. Where you can see that the x component given to us was 2 alpha x square y, and the y component given to us was 2 by 3 alpha x cube plus beta y. Something like this was going to us. Now, if f is conservative, then f should be equal to negative gradient of some kind of potential energy, which means that our x component should be minus del u by del x and y component should be minus del u by del y. In other words, minus del u by del x should be this one, 2 alpha x square y. So that means or we can say that du is equal to minus 2 alpha x square y dx. Okay. Provided dy is 0 or y is constant. So we can do an integration kind of thing over here. We can say that equal to where y is a constant. Suppose at x equal to 0, the potential energy is some u naught, and at x equal to x, the potential energy is some u. You'll get u minus u naught is minus 2 by 3 alpha x cube y, because integration of x square dx, you're doing that. Rest of the terms are just coming outside. So this 2 alpha y is just coming outside. Okay. Plus, now instead of a constant, we'll write it as a constant as, okay, so this is C1 is a constant or a function of y, because y is also constant. So this is what my first equation is. So you can absorb this u naught within that constant. You can say that, okay, our u is equal to minus 2 by 3 alpha x cube y plus some kind of a constant of plus some kind of a function of y. This is what we are getting from fx equal to minus del u by del x. Now let's see what we are getting from fy. The y component of force was 2 by 3 alpha x cube plus beta y. So minus del u by del y was equal to this. That means du is equal to minus of this whole thing into dy, keeping x as a constant. So again, if we integrate this from something to a bi-coordinate y. So this time what we'll do is we'll integrate with respect to y, treating x like a constant. So our potential energy function will come out to be minus 2 by 3 alpha x cube y plus, or rather minus, so minus beta by 2 y square plus some constant, but that constant is a function of x. It's a function of x. So, I mean u minus u naught. So again bring the u naught that side. So this becomes from equation 2. This. So now combining fx equal to minus del u by del x and fy equal to minus del u by del y. So there what we had got was potential energy was this kind of function. It was minus 2 by 3 alpha x cube y plus some kind of a function of y, and from here we got that it is minus 2 by 3 alpha x cube y plus or minus whatever beta by 2 y square plus some kind of a constant of which is a function of x. This is the relation we're getting. Okay, so hope these steps are clear to all of you. Aside relation method. Now you can see that left hand side can be equal to right hand side for LHS to be equal to RHS. Okay. C1y should be equal to minus beta y square by 2 plus some constant. So this was C2. And C2y, C2 as a function of x must be a constant. Should be independent of x. So this is the only way these two equations will be satisfied. So that means my potential energy function is basically something like this. It is minus 2 by 3 alpha x cube y minus beta by 2 y square plus some constant. And now you can see that work done by F will be negative of delta U. So A to C was the point 0, 2, right? And C was the point 3, 0. So independent of path, work done by F will be minus of potential energy at C minus potential energy at P. Now from that potential energy function, you will see that potential energy at the point C, which is 3, 0, will be equal to minus, which I think the coordinates are wrong with it. I think the coordinates are fine. So the potential energy at 3, 0 is just C. And the potential energy at E, which is 0, 2, is, so this term becomes 0. So it becomes minus 2 beta plus C. Therefore, you can see it becomes minus 2 via any path. So this is like solving the purpose of both part 1 and part 2 by first solving the fact that it's a conservative force and finding the formula of potential energy. So I'll just leave you with the steps for a bit. Okay, so hope this is clear to all of you. Any difficulty with the so-called partial integration? This kind of step is called partial integration. So we are keeping one variable constant and integrating with respect to the other. So if you have any difficulty with this kind of step here, where we are doing partial integration, please let me know. I'll explain further. Now, for example, if the force given to us happens to be a force which is not conservative, then it will show up in these steps. Okay, I'll just show you how something like that works. So let's see an example to understand that. So for example, suppose our force had been like this, that it was 2 alpha x square y I cap plus 2 alpha x cube j. That 3 is not there and that other term is gone. Now, is this conservative or non-conservative? So I'm sure you know, all of you know this method that del cross f would be 0 for conservative force. But let's understand actually where that comes from. Okay. So another way to understand it, if f is conservative, my fx should be equal to minus del u by del x, and fy should be equal to minus del u by del u. Now let's solve both of these partial integrations separately and see what we get. So minus del u by del x is 2 alpha x square y. So integrating this, we would get this is minus of 2 by 3 alpha x cube y plus some kind of function of y, and minus del u by del y is equal to that y component, which this time I have taken as 2 alpha x cube instead of 2 by 3. So I would get the u as minus of 2 alpha x cube y plus some kind of function of x. So now these two have to match. There has to be a potential energy formula which exists, which matches both the first condition for fx and the second condition. So it has to be such that minus 2 by 3 alpha x cube y plus some kind of a function of y should be equal to minus 2 alpha x cube y plus some kind of a function of x. So in this statement, this term should be independent of x, and this term should be independent of y. And you can see that's just not possible, because this is 2 by 3 and this is just 2. This is not possible. So you can see that, therefore, such a potential energy term does not exist. And therefore, you can say that F is non-competitive. So I'm just minimizing this to show you how this works both ways. Even if you're given a non-conservative force, you can, without using that gradient and all that, without using curl, a del cross F is called curl of a force. Without using all that also, you can quite easily show that it is conservative or non-conservative. Okay. So another way to understand the idea behind this is that if Fx is minus del u by del x and Fy is equal to minus del u by del y, then implies that del by del y of Fx is equal to how much? It is minus of and so you can see that this must always be equal to this. Okay. Because the order in which you do the differentiation doesn't matter. Del by del y of del u by del x will always be equal to del by del x of del u by del y. You can take any example and you can understand that partially differentiate with respect to x first and then with respect to y, or partially differentiate with respect to y first and then partially differentiate with respect to x. It's one and the same. Okay. So that is why del by del y of fx must be equal to del by del x of fy. Okay. For force to be equal to negative gradient of potential. Or in other words, del cross f must be equal to, or before that we can just write it like this, that before we write this step, right, like this, that del by del x of fy minus del by del y of fx must be 0 for the force to be negative gradient of a potential energy. So in other words, del cross f be equal to 0 So this thing only can later be extended to 3 dimensions also. You can understand how the curl formula works out in 3 dimensions. The forces x, y, z, all 3 components. So just go through this. Okay, people, so hope this is clear. So another way we could have done the earlier question was for that given force. We could have first step what we could have done is the force conservative? We could have checked that by saying that is del cross F 0. So del cross F would have been this. This will be. And we would have seen that yes, this is 0, it's fine. So that means the force is conservative. Therefore, F is conservative. And then we could have calculated by a very simple method. Therefore, work done from A to C for any path is equal to work done along the path ABC. So again, going back to that diagram, the path ABC, we could have individually calculated the work done from A to B, and then from B to C. So A to B, you would have seen that the displacement, differential displacement is just dx I cap. So the work done would have been fx dx. Yeah, Bhaskar, I'm coming to 3-dimensional components. Okay, so fx dx would have been our would have been fx was 2. Now, what coordinate is fixed? Y coordinate is fixed. So it is 2 alpha x square into the y coordinate, which is fixed. Dx. This would have been the work done going from A to B. So work done from A to B would have been 4 alpha x squared dx integrated from 0 to 3. that would have been whatever 4 alpha into 27 by 3, 36 alpha. This is the work done from A to B. Then B to C, the displacement would have been only along the y-axis. So the work done would have been y component of force into displacement along the y-axis. So that would have been, now the x is constant. X is constant at 3. Y is changing from 2 to 0. So this would have become 2 by 3 alpha x cube. So 3 cube plus beta y dy integrated from y equal to 2 to y equal to 0. So the first term would have given us minus of 36 alpha. And the second term would have given us minus 2 beta. You can see this would be 2 by 3 alpha into 27 into 2. That's 36 alpha, but with a minus sign. The second term would be minus beta y squared by 2. That would become minus 2. So this is what would happen. Okay, so our total work done from A to C via any path would be equal to work done along this path EDC. And this would have come out to be minus. So this is another way of understanding this. Okay. So I'll expand this to 3 dimensions, and more important 3 dimensions to both come in IIT. You'll also understand this whole operation in polar coordinate system, that is r theta system. Okay. But just first take a look at this and understand this. Okay, so people, when we expand this to 3 dimensions, life becomes much more tricky. But we understand one thing again. In 3-dimensional case, when we say that force is negative gradient of potential energy, it means that x component of force is minus del u by del x. Y component of force is minus del u by del y, right? And now simultaneously z component of force is also there, which is minus del u by del z. So if this is the case, now we have to basically understand two terms over here, that del by del y of del u by del x must be equal to del by del x of del u by del y. Now the same operation also holds true for y and z. Okay. So this is between y and z, and simultaneously it also holds for x and z. So this is like we're just using a property of partial derivative. Okay, but we are now operating that property for 3 pairs. So since this is the case, so it implies that del by del y of fx must be equal to del by del x of fy. Simultaneously, del by del z of fx must be equal to this partial gradient. So in other words, we can say that del by del y of fx minus del by del x of fy must be equal to 0. This is equation 1. Similarly, we'll have 2 other equations. And so combine these 3 equations into vector, we can say that this cross product, this is called curl of a force. This should be 0. Okay. So how to calculate curl of a given force? Just calculate this as a matrix, but the matrix has operator inside it. The first term this whole thing should be a null vector. So each of the components will give you each of those three equations. You will see del by del y of fz minus del by del z of fy I cap, and similar term, similar term. So this will give you the 3 equations when that is equal to 0. Okay. So I'm just minimizing this so you have a look at this and understand this completely. Curl is just a name beta because Basically, this is called the gradient operator. Okay. When this applies to a scalar quantity, it is called gradient of the scalar. So it makes it a vector quantity whose each component is gradient along that direction. This becomes, this gradient of a scalar becomes del by del x of that scalar I cap plus del by del y of that scalar j cap, like that. Similarly, we can also apply it to vector quantities in two ways. One is del dot f. This is called divergence. And we can also operate del cross, which is called curl. So in higher mathematics, both divergence and curl have different significances. Okay, they have different kind of significance. Divergence would be like del by del x of fx plus del by del y of fy plus del by del z of fz. Whereas curl will give us a vector quantity which is like this. So they have different significance. Now, one of the significances that you learn here is that if curl of a vector is 0, then it is a conservative quantity. That means the path integration of that vector is actually independent of path. So, for example, if we have an electric field whose curl is 0, that means it's a conservative electric field. So, potential exists for that kind of. If we have a force whose curl is 0, that means it's a conservative force. So, we can define a potential energy for that force. But if curl is non-zero, then we cannot define potential. Because again, no such function U will exist which will satisfy equation 1, 2 and 3 simultaneously on the board. So अगर तीनों equation satisfy नहीं होते, that means ऐसा कोई potential energy function exist नहीं करता. So actually the nomenclature curl comes from the fact that if the curl of a vector field, like a force or a electric field or any such field, if the curl is non-zero, that means those field lines are forming closed loops. So they curl. Whereas if it is 0, then they cannot form closed loops. Because in round path or in closed loop, the work done has to be 0. So that's one of the reasons why that is called curl. Because it gives us an idea about whether the field lines for such a field are curling into closed loops or not. Okay, so ultimately this becomes the easy way to check this operator del cross. This becomes the easy way to check even if the three-dimensional system whether a given force is conservative. Now, what I also want to work on today, show you, is gradient operator in polar system. Two-dimensional polar system. It's R theta. So how the gradient operator works in this kind of system, let's understand. Now in 2D system, let us say that a particle which was at initial position vector R like this over here has now made a small displacement which is a displacement ds. It has gone from initial position R to a final position that is like this, r plus ds. Fine. So it's gone from here to here. So that displacement, how we write in polar system, let's understand that first. So in polar system, the coordinates of this point will be given by this angle is theta, and the coordinates of this initial point are r comma theta. Whereas by the time it's come here, you can see that theta is changed by a small amount d theta. So this whole angle has become theta plus d theta. So this whole angle here, it has changed to theta plus d theta. And also the length of this line has changed from r to r plus dr. Here this length was r, now it's changed. The coordinates here have become r plus dr, theta plus d, the polar coordinates. Now in polar system, the unit vectors, as you know, we use are r cap and theta cap, radial and tangential. So in this diagram, this is my radial direction. This is the direction of r cap, and this is my tangential direction. This is the direction of theta cap, along with theta is increasing. So you can see that if you drop a perpendicular here, okay, that is your dr, and if you drop a perpendicular here, that is your r d theta. Understand? So that small displacement ds has components along r cap and r d theta along theta. So that is why in polar system, a differential displacement will be written like this: dr r cap plus r d theta, where the magnitude of this displacement therefore becomes radial component square plus tangential component square. So first of all, in polar system, this is how we write a differential displacement. We write it as if, so it's like, no, just to bring this in perspective, it's like this vector r is now changing to this vector, which has a vector, let us say, is r plus d's. But अभी इसके अगर मैं components बनाता हूँ, and this side becomes equal to this side, which is equal to r. This becomes dr, this small length from here to here, and this small length from here to here, because this is d theta. So this becomes r d theta, which is small. So therefore, you can see my displacement vector, which is this vector over here. Therefore, you can see my displacement vector is becoming that kind of thing. Change in length along r cap plus the rotational effect. So it has a small tangential displacement, like a circular displacement of r d theta. If something is moving only radially, then it only have this radial component, and d theta will be 0. Okay. So only radial movement that is no angular motion. So no angular motion means d theta is 0. So your ds will be only dr r. Whereas if we had the case for only tangential motion, that means r is constant. That is circular motion. In circular motion, the differential displacement is r d theta. That's why the velocity is r omega. But in general curvilinear motion, that becomes this. Okay. So I'm just minimizing this for a moment. Just get used to this idea. Then we'll see how this relates to us for gradient, which we are going to look at next. How to apply the gradient operator in r theta system. Okay, so this is how the differential displacement operator applies. Okay. So now, while that body is moving, if there's a force acting on it, so now while that particle is moving, it's moving along some kind of path like this, and at some instant, its instantaneous position was here. So its position was here, and now there was some kind of a force also acting on it. There's a force F acting on it while it's making a differential displacement ds levels. So the work done by that force will be F dot ds. So that now in this term, both F and ds will be written in terms of radial and tangential components. So it is Fr r cap plus F tangential theta cap dot product with ds that we just saw. You have to write it in this, okay? Where you can see this is the force is radial component, and along this direction the force is tangential component. So again, this is your r cap direction. This is your instantaneous theta. So the polar coordinates of that point are r theta. When it's at the polar coordinates, so this work done becomes Fr dr plus F tangential into r d. This becomes okay. So you can see that if the force is conservative, then you can define potential energy such that it is negative of work done by this. So minus of radial component into dr plus tangential component into rt. So now reverse this equation, that du is equal to this. So in this equation, if we keep d theta as 0, that means we are keeping theta as constant. So that's the only radial movement kind of. So if we are doing that, then du becomes minus radial component to dr, or radial component minus del u by del r. And similarly, if we are going with only tangential motion, then your dr term is becoming 0 in that expression. That's the second part of it. If on the other hand, if PR is 0, that is R is constant, so we are giving tangential motion, then du is minus of F tangential into RD. So the reverse of this becomes that F tangential becomes minus 1 by R del U by del theta. Why we are changing it to del by del instead of perfect derivative is because we are keeping this condition that over here R is constant. We are applying this condition. So this becomes partial derivative. Here we are applying this condition that theta is constant. So then we can say overall that the force is minus del U by del R cap minus 1 by R del U by del theta. Okay, so this is how the gradient operator applies in polar system. In fact, before we can also see that we can say that the force is negative gradient of potential energy. The potential energy here is a function of r theta, and the gradient operator is del by del r cap plus 1 by r del by del theta. So when it applies, it is this. We'll see a couple of practical examples of this also, and you'll understand. But this is how we relate the relationship between potential energy and force and the gradient operator. More importantly, this is how we relate this in polar system. So you would have seen this relationship, for example, in the relationship between potential and field due to electric dipole. The potential is given by P cos theta divided by R square. So you get radial and tangential component of electric field from that. So this is how that formula actually comes. Okay, people. So hope this part is clear. So from this point onward, you can just remember, keep in mind this formula. The gradient operator in polar system, it applies like this. Now, one more thing we should keep in mind is the interrelationship between rectangular or Cartesian system and polar. That is very simple, that if you have polar, then correspondingly x is r cos theta and y is r sin. And if you have this, then correspondingly r is square root of x square plus y square, and theta is tan inverse of y by x. That is obviously there, but also I cap and j cap want to convert. So r cap becomes cos theta I cap plus sin theta j cap, and theta cap becomes minus sin theta I cap plus cos theta. So fairly obvious things you would have seen in applications like circular motion, and this is simply because if this is your r vector with respect to your x-axis, the reference angle is taken as theta with proper sign convention that anti-clockwise is positive. So your r cap and theta cap are just unit vectors which are like this. R cap is the unit vector along this direction, and theta cap is the unit vector along this direction. Here r cap is like this, and theta cap is like this with respect to x, y axis. So that's how it is. So sometimes this interchangeability is also important for us. So for example, you have a question like this, that the potential is given by the function, let us say alpha upon x square plus y square plus beta x upon root of x square plus y square. Now you want to find the electric field magnitude at the point, let us say 3, 4. Okay. And let us say potential is in volts and x, y are in meters. X, y is given to us in meters. Now you can see that if you go for the Cartesian system here, you can solve, but it's very lengthy. Can't you see it? Because the differentiation, the partial derivative, especially for the second term, will become very lengthy. So if you go with Cartesian system, you will express electric field x component as minus del v by del x, y component as minus del v by del y, and then the magnitude of electric field at any point will become square root of x square plus y square. This is solvable, but this is very lengthy, okay, because you have this relation between electric field and potential. But on the other hand, if you go with polar system, it becomes very simple. You can see that in polar system, the potential that you have written as alpha upon x square plus y square plus beta x upon square root of x square plus y square. This is just becoming alpha by r square plus beta cos theta. This becomes this function. This becomes this. Okay. So your field, which is negative gradient of potential, is such that radial component is minus del v by del r. So that will become how much? Negative of gradient of this, so that will become alpha by r. And your tangential component, which is minus 1 by r del v by del theta, will just become beta by r sin theta. Your field, oh sorry, this will be r cube. You're differentiating by mistake, so this will be 2 by r cube. 2 alpha by r cube r cap plus beta by r sin theta. That's all. So now we'll come to how to calculate the field at that particular point also. That will be very easy. You will just convert that point to polar system. But important thing is you understand this image. This how it is coming. It is coming from the fact that gradient in polar system is del by del r cap plus 1 by r del by del theta. It becomes extremely handy in a situation like this. And here, of course, I'm using that relation. R is root of x square plus y square. Cos theta is x upon r. Sin theta is y by r. I hope this is clear to all of you. Now all you have to do is that the point I had given you 3, 4, उस पे r का value निकालना है और sin theta का value निकालना है, which you can see very easy. 3, 4 has the polar coordinates of r equal to 5 and theta equal to 53 degrees. X, y equal to 3, 4 means that your distance from the origin r is equal to 5 units and your angular position tan inverse 4 by 3 in the first quadrant is nothing but 53 degrees. But similarly, had it been minus 3, minus 4, then it would have been in third quadrant. So your angular position would have been 180 plus 53. Okay, so now, for example, at the point 3, 4, your r will become 5 and your theta will become 53. If it was, for example, minus 3, 4, your r would still be 5, but your theta would become, so it would become second quadrant. So it would become 180 minus 53. It would become 127. So you substitute r and theta over here and you get the components. Now from that you can get the magnitude of electric field as your radial component square plus tangential component square plus 1. So you put this value of r and theta here, so you know each of these components and you substitute that in this formula, you can find the magnitude. Whereas if you want to find an I cap j cap notation, you can still do that, but replace I cap and theta cap with those unit vectors. Cos theta I cap plus sin theta j cap. For this point, you can also see that your r cap will be cos 53, which is 0.6 I cap, plus sin 53, which is 0.8 j cap. And your theta cap will become minus of 0.8 I cap plus 0.6. So if you want to find out finally in I cap j cap notation also, you can replace everything here. You can get it in I cap j cap. So this is sometimes a very useful way of solving questions. See, Bhaskar, to answer your doubt, which you just sent me about gradient and curl, to understand gradient is something that operates on a scalar quantity. It has a very basic definition that if I say a scalar quantity depends only on x, okay, like y is a function of x, then its gradient is nothing but its rate of change with x. So, for example, you have potential energy which is only a function of x for a one-dimensional function. So that means that force has only one component along the x-axis. Okay? So that x component will become minus du by dx. So that's how the gradient. But if you have a function of more than one variable, then what we mean by gradient is rate of change. So for example, so to understand this properly, the difference between what is divergence and what is, or rather what is gradient and what is curl. Gradient का मतलब actually क्या होता है? We want to understand this. Okay. How this gradient operator, when it applies on a scalar function, let's say this function is of two variables x and y. So it gives us what is called gradient of that. What it means. So the gradient is nothing but rate of change. So it is some kind of a slope. But you have to understand here, the function is a double variable function. So how do we actually visualize slope? So that is the thing you have to now understand. Okay? That suppose you do a three-dimensional system where your function is the z coordinate, is a function of x and y. Okay? So now you drew your three-dimensional system x, y, z like this. Okay. Now at any particular point x comma y, you'll have a particular z coordinate. So you can think of a building of that height. That is the z coordinate. Okay. So at various different points where you draw this, the collection of points that you get x, y, z, that will give you a surface. Okay. So the collection of points that you get, that will give you a surface. Okay. Now, if you go from one point x, y, z, okay, to another point x plus dx, y plus dy, z plus dz. So your displacement vector has become dx I cap plus dy j cap plus dz t cap. It becomes like this. So what do we mean by rate of change of the function f, or basically gradient of z in this case, because we have related z to that function. So we are thinking of some kind of slope, okay, but it's a two-dimensional curve. It's a two-dimensional surface. Huh? So here z is a function of x, y. So in terms of geometry, z is a surface. Okay, with respect to x, y. So if I make a displacement only along the x-axis, so if dy is equal to 0, then my displacement is dx I cap plus dz k cap along that surface. So what is the rate of change? It is ds dz by dx, but keeping y constant. Okay guys, just hang on a minute. My software is just giving me some trouble. I'll have to relaunch my whiteboard software. So just take a minute's break. I will just relaunch. We'll start again. So just take a couple of minutes break. I'll have to probably reboot my other PC. Okay, people, so back online. So what I was saying is that if we have a function which is a two variable function. So let us say we are saying the z coordinate at a given point is that function. So when we plot this, when we plot z as a function of the two-dimensional plane, so what we get is z becomes a surface, represents a surface where every point x, y, z satisfies the relation z is equal to f of x, y. So for example, if z was, let's say, root of r square minus x square plus y square, then it would represent a spherical surface. So if I take only the positive x and y, I mean positive values of z, yeah, I'm not taking the minus 2, so it represents this hemisphere. So z represents this hemisphere where this diameter and this diameter are your x and y axis respectively. Okay. So now what is happening is that if we make a small displacement along that surface such that in the first case we put dy as 0, so we get dz is equal to some kind of gradient that becomes this. So this gradient actually becomes what? It becomes a type of a slope, but a slope of what? So that's what we have to understand. So if we are making a displacement such that our y coordinate is not changing, that means what we are basically doing is that imagine that surface. So again, this was our z axis, this was our y axis, and this was our x axis. Now it's a three-dimensional surface like this. Now suppose I'm moving along the surface such that my y coordinate is not changing. That means I'm cutting it by a plane which is parallel to the xz plane. To cut this surface by a plane which is parallel to the xz plane. So at the point x comma y comma z, cut the surface which was z is equal to function of x, y by a plane parallel to your xz plane. So then what will happen is that that plane will cut the surface. It will give an intersection which is a curve, okay, on that plane. Okay. That surface and the plane will cut a curve or will intersect to form a curve which is on that plane with which you have cut. Okay. So that slope of that one at that point is nothing but del z by del x, because that plane is basically what? It's parallel to the xz plane. So that curve that it cuts, that intersection curve that it cuts, it is z as a function of x, because y is constant on that plane. Okay. So that is the meaning of it actually. That is the meaning of that component of the gradient. Okay. Now similarly, if you cut it with a plane which is parallel to the yz plane, then your x coordinate is fixed on that. So the slope of the curve that you will get. Okay. So similarly, for a displacement ds, which is just dy j cap plus dz k cap on the surface. That means cut the surface with a plane parallel to YZ plane. So on that plane, what is happening? Dx is 0. Okay. So it will intersect to form a curve. That curve will represent z as a function of just y, because x is now constant. So the slope of that one is nothing but your del z by del y. So that is why we say that the slope, okay, or gradient of z, which is the function of xy, has 2 dimensions now. Okay. And therefore, it becomes a vector quantity, such that so this is the meaning of the term gradient. So Bhaskar, to answer your question, the fundamental meaning of the term gradient क्या होता है? It is a 2-dimensional slope. If it is a 2-dimensional function. Similarly, if it's a 3-dimensional function, we can't really plot it because we don't have any system of plotting a 4-dimensional graph. But you have to now visualize it that way, that that function is varying with all 3 spatial coordinates x, y, and z. So it has a rate of change along all directions. So the gradient is a vector quantity such that each component of that vector is giving you the rate of change with respect to that particular direction. Whether that is in terms of ijk or it is in terms of r theta phi, or in 2D it is just xy or r theta, whatever be the case. So that is the meaning of the term gradient. Gradient in general means rate of change with respect to position. So if it's single dimensional function, then it's just d by dx. But if it is multiple variable function, it becomes like this. Whereas curl is something else. Okay, so let's leave you with this whole analysis for a moment. Understand this properly. Okay, so ultimately gradient is an operation on a scalar which gives its slope, or what we call gradient, as a vector quantity, such that each component of that vector is equal to slope along that direction. Each component of that vector is You can see slope along x-axis, slope along y-axis. That is the meaning of the term gradient. Whereas curl is a different type of operation. Curl, what we've seen earlier today, is an operation like this. It applies to a field or a vector. Curl operates on a vector. For example, you have a single charge. You can see the electric field is like this. So the electric field is given by kq by r square r cap. So if you were to see this on a 2D plane, so suppose you have kept the charge particle on a 2-dimensional plane, and you just want to see in 2D, you can say that the electric field will become kq upon x square plus y square to the power 3 by 2 x I cap plus y j cap. So you can see that when you do del cross E, it will come out to be 0. Definitely, because you can see electric field's x component is kqx upon x square plus y square to the power 3 by 2. And electric field's y component is kqy upon the same thing r cube. So when you do that del cross operation, you can see it will come out to be 0. Or you can also use in 2D, you can also do del cross E in this way. It is del by del r, 1 by r del by del theta, radial component, tangential component. So you can see the tangential component is 0 and the radial component does not have any. So here in this case of electric field, it is kq by r square r cap. That means the radial component of field is just kq by r square and the tangential component of field is 0. So when you substitute this over here, you can see you get 0. Okay, so that's another way of understanding how the curl is becoming 0. So what that is showing us that the electric field lines are such that they don't curl. Okay. Now same thing if you do in 3D, you write your electric field vector as kq x I cap plus y j cap plus z k cap upon x square plus y square plus z square to the power 3 by 2. So here, for example, your x component of field become this. Similarly, your y component will be this. Your z component will be this. So again, you can see that your del ex by del y is the same thing as del ey by del x. Your del ey by del z is the same thing as del ez by del y. And your del ex by del z is the same thing as del ez by del x. So this property holds consistently. So you can see that your curl, the vector, will be 0, which means that it is a conservative field. So the fact that curl is 0 means that E dot ds in a round trip must be equal to 0. So it should be conservative. Because the field lines are not curling. The field lines are emanating from positive charge and either going to infinity or they might be terminating at a negative charge. But they are not forming closed loops. So field lines do not form closed loops. Whereas, for example, if you visualize the field lines which are created due to time varying magnetic field, Suppose we have a magnetic field like this inside a solenoid. Which is something like this. P is equal to alpha T minus K. So there we know that you have electric field lines which are in the form of circles. The circular field lines. If alpha is positive here, then the flux going into the plane is increasing. So it will create anti-clockwise electric field lines. So here your electric field lines will be like circular loops. So you see that if you calculate del cross E, it will come out to be non-zero. Be non-conservative. Which you can calculate and work out, okay? Because you know how to find out field at a position R. It's tangential field like this. So you just use that system and work out the curl, and you'll see that it's a non-zero quantity. The field at a point like this will actually be some function of R, theta cap. So the moment that that happens, you can see its del cross will not be equal to 0. So it has to be non-conservative. So this is one way of understanding this. Okay, people. So hope the concept of gradient and curl is clear to you, why they're different. And there's also a third term called divergence. Okay. Now see, in JEE typically we don't get too much into the geometrical meaning of divergence and curl and gradient. In fact, the whole operation is not part of your math syllabus. Gradient operator is not part of your math syllabus. It is only that in physics in certain areas it becomes unavoidable to use it. So we teach it to you in physics and you understand it this way. In engineering second semester, you will learn more about this and it's very interesting. And you will also understand the significance of vector analysis in n-dimensional space, not just 2 or 3, but n-dimensional space, which is like really a huge leap in terms of imagination and all that. Okay, so that's a very difficult part of your engineering courses. Vector spaces in n dimensions or something like that. The course is called. It's one of the more difficult courses, especially in IIT and all. Anyway, now coming back to this, we have time for probably one more question, so we'll discuss. Now, some of you were asking me about the concept of center of charge and when it can be applied. So I'll take an example and explain. So supposing we have a situation like this, that we have something like, let's say, a cylinder. So this is the cross-sectional view of a cylinder made of some kind of non-conducting material, which is lying on a rough surface like this. So this is a rough surface, and this is a, let's say, a wooden cylinder of mass m and radius r. Now the cylinder has got, and its length is also L. So three-dimensionally the cylinder is like this, lying on a surface like this. So now this part of the surface has got positive charge. So it's got plus sigma, and this part of the surface has got negative charge. It's minus sigma. So quarter parts of the cylinder's curved surface have uniform surface charge distribution. Plus sigma and minus sigma, as shown. That is the case. Now, this is our gravity's direction, and we are taking x-axis like this and y-axis like this. Now, what's happening is initially the cylinder is at rest. at the position shown. When at t equal to 0, a uniform electric field E naught I cap is switched on, such that Q E naught is equal to d by 4 mg. Actually, forget this. We don't need to relate it with mg. Yes. Now assume sufficient friction to prevent slipping. So you have to find the torque due to electric field and the angular acceleration and the linear acceleration of center of mass just after t equal to 0. And you have to also find VCM's maximum value after t equal to 0. Assuming that there is a uniform electric field present all the time after t equal to 0. Okay. So through this question, we'll understand how we can use the concept of center of charge. Okay. So just try this out first. Start by understanding how much torque the horizontal electric field E naught I cap will create on this. Net force, of course, because of electric field will be 0 because we have equal and opposite charge. Yeah, effectively the center of charge will be as if it's inside its volume. Correct, Master. Now, there's one very easy way to prove that and understand that. See, for example, when do we say that center of gravity is at the center of mass? When there is uniform gravitational field. Okay. And when that happens, we say center of gravity is the point through which the net gravitational force acts. Okay. Or torque due to gravitational force is 0 about center of gravity. So now just replace the term gravitation with electric over here, electrostatic, then you'll understand. So when we'll say center of charge is the point through which the effective electrostatic force is acting whenever the electric field is uniform. Okay. So we'll apply it in two parts over here. So one is when you look at the three-dimensional picture. Now just imagine on the surface any thin strip like this. So this thin strip itself is having a distributed charge now. So now if I switch on an external electric field, which is in this sort of direction, parallel to the surface on which it is lying, to this surface, okay, what will happen? Each element here will experience small force vectors like this. So if this strip is having a total charge of dq, that is charge on the strip, then the net electrostatic force acting on it will be acting through its center point, and that will be dq into. So net electric force, electrostatic force on the strip dq acts along electric field, but through its midpoint. Okay. So this itself I am using the concept of center of charge. Why? Because it's uniform electric field and uniform distribution of charge. So center of charge is the point C. Why? Because I have two things: uniform electric field and uniform charge distribution signal. Okay. So this is the first thing in which I am applying center of charge. Now next, when I put the strips all together, also I'll apply center of charge. So that way I won't have to do any integration at all in this problem. Okay. So next you'll see what's happening here is if we make a cross-sectional free body diagram kind of thing. Because dipole se top milega na. So you can do the question in two ways. One is now you can use integration and take one pair of such strips and show that they are collectively acting like a dipole. Or you can use center of charge method. Both are equally okay. So I have horizontal electric field E naught like this. Okay. So now if you take a pair of elements like this, so this will be experiencing force like this, and this will be experiencing force like this. So together they will create a torque like this. Okay. So dF is dq into E naught. dq into E naught. This is at an angular position theta. This differential torque it will create is 2 times dF r sin theta. Now that dF will become, so tau will come from integration of 2 times dq E naught r sin theta. Sigma into L into r square will come constant outside. We will have sin theta d theta integrated. because your dq will be sigma into dA. It will be sigma into L into R d theta. And theta, as you can see, will go from 0 to pi by 2. So the torque will become 2 times E naught sigma R square L into 1. This will become the torque because of the electric. Now another way to calculate this is, so another method, center of charge method. Of doing the calculation for torque. Now what we do is, all the charge that is located here, to take small strips at a time, you can see that they are all experiencing small force vectors which are like this. Okay. So it's going to be effectively is going to be the force like this, Q into E naught like this, where Q will be the total positive charge. So that is sigma into 1/4 of 2 pi RL. And by symmetry, this will be along the 45-degree angle, where this distance d will be how much? Use that formula for center of mass. So d will be, oops, just a minute, my software is again hanging. Just give me a minute, guys. So this happens because of Zoom. It happened because of the software. So yeah, d will become r sine 45 divided by pi by 4. So that is that correct? Okay. Now similarly, this charge, the negative charge here, will be experiencing force vectors which are like this. So cumulatively, that will be equivalent to a minus q charge here, experiencing a force like this. Okay. You can even actually convert it into a dipole. So it's effectively a dipole, which is like this, in an electric field which is like this. So you can also do it this way, that the dipole moment vector here will become 2 times q into d, which is 2 root 2 r by pi. Okay. And this will be along this unit vector, I cap plus j cap by root. So your dipole moment vector is becoming 4 qr by pi, if I'm not mistaken, into I cap plus j cap. Okay. Now electric field was E naught I cap. So your P cross E will become 4 qr by pi E naught into j cross I, which is minus k. So that's fine. And now you can also see that the magnitude of the torque is this, and just substitute the value of q, so you get the same thing that you got earlier, 4 qr by pi e naught. So that is 4 into 1/4 of sigma into 2 pi rl r e naught by pi. So pi cancels off, and what we are left with now, 4 cancels off, so 2 times sigma r square l. So this is the torque. So this comes out like this. So which is the same thing as what we had got by the integration method. But this becomes much more shortcut, provided you remember the formula of center of mass for a quarter. We have used center of mass of quarter disk actually. नहीं disk नहीं use करेंगे बेटा. You have to understand something over here. The formula that we use not for center of mass of a solid quarter disk like that. It's not that. We have used for this, because the charge distribution is like what? It's like this. So the formula of center of charge is basically center of mass of an arc of 90 degrees. Because even though mass wise the distribution is a solid cylinder, but charge wise the distribution is not solid cylinder, it's only on the surface. You understand me? Okay. So this is giving you the same result that we got here. Good. So just remember that when you are relating center of charge with center of mass, to relate, don't see how the mass is distributed, see how the charge is distributed. Then say that okay, if we had mass distributed in the same way like the charge is distributed, then उसका center of mass कहाँ होता है? तो यहाँ पे charge surface पे है, positive charge वो quarter surface पे है, तो imagine such a mass where its center of mass will be only on the surface and quarter part of the cylinder. That becomes the position of the center of charge. Okay, and once you got the torque, rest of it is rotational mechanics, which I'm sure all of you are quite experts at. We finish the problem anyway. So on the cylinder, the moment we switch the electric field on, it creates a torque like this, and that creates a frictional force like this, apart from normal reaction and weight, of course. Okay, so just write down the equations while my software takes its own sweet time. Anyway, so friction will give the center of mass a linear acceleration, and it will kind of cut the angular acceleration a bit. So we'll have tau minus friction into r is equal to I alpha, and friction is equal to MAC, and this condition for no slipping. So when we substitute that, we get tau by r will become m by 2 plus m times c. So 2 sigma r l e naught will become 3 by 2 mc. This is just at that moment when the torque is that much. Now for the next part, what we can do is we can use work energy. As it goes from this position to this position, where it's now like this. Okay. So here the dipole moment has become like this. Here the dipole moment was like this. So this is the stable equilibrium position. So this is where its kinetic energy was 0. This is where its kinetic energy will be maximum. So work done by the torque from theta equal to 45 to theta equal to 0 is equal to the change in kinetic energy of rolling. Or you can use that formula of potential energy of a dipole, which you would also derive from this concept. That PE into 1 minus cos theta kind of term, that one. You can also use this, or delta U plus delta KE is 0, where U is potential energy of a dipole in an electric field. This kind of term. Okay. So our initial potential energy was PE 1 minus cos 45, or whereas our final potential energy is at theta equal to 0. The kinetic energy is maximum. This was at theta equal to pi by 4, the initial value. So this becomes 0. So half mv square plus half I omega square maximum value becomes PE1 minus 1 by 2. And from this you can calculate. Now further you can write this as, it's a cylinder. So this will be half mv square 1 plus half is equal to. So from this you get the Vmax. Okay people, so that is a good example of an application of center of charge method, okay, where you're borrowing on the concepts you've learned on center of mass. So just like when a body is in a uniform gravitational field, the center of gravity is the same thing as the center of mass. Okay, and the effective gravitational force, you can say, acts through the center of mass. So same way over here, if charge distribution is in a uniform electric field, then the effective electrostatic force acts through the center of charge. And plus, if the distribution of charge happens to be symmetrical, then the center of charge will be equal to the this thing. So Bhaskar, to answer your question, if the charge had been inside the cylinder over here, okay. So for example, if we take a cylinder where, let's say, you have charge, half of it is charged with a volume charge distribution, then center of charge will be according to the center of mass of a volume distribution of mass. It will be like that. Okay. So hope this is clear, people. Okay. So with that, we come to a conclusion of today's lecture, and I will be sending you the notes as well as the video. So don't worry about if you missed out some notes and all that. And just continue sending your doubts to me, preferably personally on WhatsApp, otherwise on the group. The only thing in the group is then, if there are too many messages, then some important group messages might get missed out, like lecture timings and all that. But that's okay. I mean, you can send on the group also. So I've been sending you hints about some of the questions. Hope that has worked out. In case you have not been able to solve using the hints, please let me know, because then I will solve those questions in the next lecture, definitely. Okay. That's it for today, people. All the best and stay safe.